In this lecture, we proved that if f is a Möbius transformation from the extended complex plane onto the extended complex plane, then the cross ratio of four distinct points is invariant under f. This means that the cross ratio of four distinct points z sub 1, z sub 2, z sub 3, and z sub 4 is equal to the cross ratio of their corresponding images under the mapping f. In a previous video that we had created titled Möbius Transformations Invariance of the Cross Ratio 1, we had shown that this is certainly true if either the z sub i's or the f of z sub i's, or both, are all finite complex numbers. The result does allow for the possibility that the point at infinity is one of the z sub i's or one of the f of z sub i's, but not both. We are including a link to that video in the description of this lecture. In this video lecture, we extend the result to allow for the case where the point at infinity is one of the z sub i's and also one of the f of z sub i's. In the video Möbius Transformations Invariance of the Cross Ratio 1, we had broken down the proof into two main cases. In case 1, neither the domain nor the range of f included the point at infinity, so that the z sub i's in the domain and the f of z sub i's in the range were finite complex numbers. In the second case, one of the f of z sub i's was the point at infinity. We had chosen without loss of generality f of z sub 4 to be infinity. All the other points remain finite complex numbers. There was a third subcase, which was a mirror image of case 2. This time, one of the z sub i's was infinity. We had chosen without loss of generality z sub 4 to be infinity. All the other points are still finite complex numbers. For this current video, we consider two additional cases. In case 4, without loss of generality, we set z sub 4 equal to f of z sub 4 equal to infinity, so that f of infinity is mapped onto itself. In the fifth and last case, f of infinity is not infinity. Without loss of generality, we choose z sub 1 to be equal to infinity and map z sub 2 to infinity. Since f is a Möbius transformation, f of z can be written as the quantity a times c plus b divided by the quantity c times z plus d, where a, b, c, and d are complex numbers, and the discriminant ad minus bc is not equal to 0. The cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4 is given by this formula. And we have the corresponding formula for the cross ratio of the f of z sub i's. We start the proof for case 4 by finding a formula for f of z, given that z sub 4 and f of z sub 4 are both infinity. In another video lecture that we had created, the title of which is Möbius Transformations Examples Involving the Point at Infinity 2, we had shown that under this condition, f of z can be written as a times z plus b. We are including the link to that video in the description of this video lecture. Observe that here c equals 0 and d equals 1. And because ad minus bc is non-zero, a cannot be 0. Since z sub 4 is infinity, we interpret the cross ratio of the z sub i's as the limit of the cross ratio of z sub 1, z sub 2, z sub 3, and z as z tends to z sub 4 or infinity. We treat the cross ratio of the f of z sub i's in the same way. We replace z sub 4 by z in the cross ratio of the z sub i's, and we focus on the fraction z sub 2 minus z divided by z sub 1 minus z. Z sub 1 over z and z sub 2 over z will both tend to 0 as z tends to infinity. Minus z over minus z has a limit of 1. And so the cross ratio of the z sub i's is equal to z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3. Using a similar idea for the f of z sub i's, one can check as an exercise that the cross ratio of the f of z sub i's is equal to the quantity f of z sub 1 minus f of z sub 3 divided by the quantity f of z sub 2 minus f of z sub 3. f of z sub 1 is equal to a times z sub 1 plus b. F of z sub 3 is equal to a times z sub 3 plus b. And f of z sub 2 is equal to a times z sub 2 plus b. Therefore, the cross ratio of the f of z sub i's when simplified equals z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3, which is the cross ratio of the z sub i's. And we have the proof for case 4. We start the proof for case 5 by again looking for a formula for f of z under the condition this time that z sub 1 equals infinity and that f of z sub 2 is infinity. Since f of z sub 2 is already infinity and since Möbius transformations are 1 to 1, f of z sub 1 cannot also be infinity and has to be finite. We set f of z sub 1 or f of infinity equal to some complex number w sub 1. Then, using an idea from the video Möbius transformations examples involving the point at infinity 2, f of z with these conditions can be written as the quantity w sub 1 times z plus b divided by the quantity z minus z sub 2, where a equals w sub 1, c equals 1, and minus z sub 2 equals d. We again apply limits to find the cross ratio of the z sub i's when z sub 1 is infinity. The limit of this fraction, as z tends to infinity, is 1. And so we take the cross ratio of the z sub i's to be z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3. Similarly, with f of z sub 2 being infinity, we take the cross ratio of the f of z sub i's to be the quantity f of z sub 1 minus f of z sub 3 divided by the quantity f of z sub 1 minus f of z sub 4. We determine f of z sub 1 minus f of z sub 3 and f of z sub 1 minus f of z sub 4. F of z sub 1 is w sub 1. F of z sub 3 equals the quantity w sub 1 times z sub 3 plus b divided by the quantity z sub 3 minus z sub 2. This simplifies to the quantity w sub 1 times z sub 2 plus b divided by the quantity z sub 2 minus z sub 3. We get a similar expression for f of z sub 1 minus f of z sub 4. We divide f of z sub 1 minus f of z sub 3 by f of z sub 1 minus f of z sub 4. W sub 1 times z sub 2 plus b is non-zero and should cancel out. W sub 1 times z sub 2 plus b is non-zero since it happens to be minus the discriminant AD minus BC, which is non-zero. And we are left with z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3, which is the cross ratio of the z sub i's. And we have the proof for case 5.